Okay, so hi everybody, welcome to our midterm review on C and memory, right? So right now the time is 8:10 and let's get started. Just as another reminder, for the people who are online, the people who are on Zoom, please post your questions to the ed post, and the ed post should be linked in chat. I'll paste it again in chat. That's the ed post. Please put your questions there. Okay. So let's get right into it. C and memory. Oh, and I forgot to mention I'm here with my AI. Liam is here, and he'll be helping present the last concept, call, and he also helped work on the slides. So thanks to Liam. All right, so let's get started. So before I get into like any of the concepts, I mentioned this in my previous review session. You should think before problem solving, right? So a lot of times, like we see a question and we're like, oh shoot, what do I do? Like, what do I have to do? What do I have to write down? And we forget to like think about the problem, right? You can only give a solution if you know the problem, right? So first thing you should think about is what is the goal or your expected behavior, right? Then once you know your goal, what variables are important for your solution? What variables are important, right? And once you identify the variables that are important, you just identify the repeated patterns. And then usually in the code, this will involve a lot of looping, right? And then you clearly identify your program logic. So you think about what your solution would entail and try it out on like small sample cases, right? So try out your base case, try out the case immediately above the base case, and see if it works. Just try it out, and if it doesn't work, then you can start over, right? So think about this before you're problem solving. Okay, I'm gonna mute just for a second to adjust my mic. Okay, so for the people on Zoom, can you still hear me? Can you guys still hear? You can just type like yeah in chat. Okay, cool. So everyone can still hear me. People in person still audible? Good? Awesome. Okay, let's continue. So let's get straight into our first subtopic, which is pointers, right? So variables and pointers in C. So one major concept in C is the idea of memory, right? And memory is just storage with address labels. So memory, you just have a place to store some values, and then each value will have some associated location, right? Some associated address. So each value has an address. That's a key idea in memory. Okay. So explain what the following expressions do in C. What does this expression do? Uh, for the people in person, you can just raise your hand. And if you're on Zoom, feel free to unmute and just say the answer. In the back? Uh-huh. Uh-huh. Yeah, exactly. So basically, we're just allocating some space for an integer, and the name of our variable is x, right? So that one's pretty simple. Variable x, for the purposes of our class, holds 4 bytes, and it represents an integer, right? Each integer is 4 bytes. So what does this code do? Int star z. Any ideas? Either from Zoom or in person? Yeah, go ahead. Yeah, exactly. And how large is a pointer to an integer? At least for this class. Yeah, 4 bytes. So variable z holds 4 bytes, and this just represents a memory location, right? It represents a memory location. Okay. A memory location is the same as an address, is the same as a pointer, right? So you can think of a pointer, you can think of a memory address, memory location, they're all the same, right? And this location holds an integer, right? That's all that it's saying. Z is a pointer to an integer. So if you follow where the location points to, it'll hold an integer, right? Okay, so what is this code doing? Int a equals star z. Any ideas? Yeah, go ahead. Yeah, exactly. So basically what was said was that z holds a location, right? A pointer. Star z gets what's at the location, and what's at the location is an integer, right? And then we just put that integer value into variable a, right? Okay. How about this one? Int pointer b equals and x. What is this? What does this and symbol do? What is this and symbol doing? Any ideas? If you're on Zoom, you can feel free to unmute and just say it. And again, it's okay. Oh, yeah, go ahead. Yeah, exactly. So what was said was that basically x is some variable, right? And then and x is the location of the variable. Okay. And then we just take that location and we put it, store it as b, right? B is of type pointer to an int, so it holds an address slash pointer. And b points to x. B points to x, right? So now if we do int y and then y equals dereferenced of x, remember? X is an integer and not a pointer, so you can't dereference it. So this code would crash if you do int y and then y is equal to star x, right? This would crash because you can only, it only makes sense to dereference a pointer, right? Dereferencing is basically you have a pointer and you get what's stored at the pointer. But x is an integer, so it doesn't work. But the flip side is this code, which will work. Why? Because in this code, we're casting x as a pointer using the parentheses int star x. So now x is being treated as a pointer. And now that we have a pointer, it makes sense to dereference it, right? Yeah, go ahead. Yeah, exactly. Yeah. So like, let's say x held 32, right? Then it would find whatever is in memory address 32 and then put that value in as y, right? Chat. For anyone posting in chat, I am not checking chat for this session. If you have questions, please post it on Ed, and the Zoom link is in chat. Okay. So let's think about our diagram, right? Okay, let's think about our diagram, right? So we have this code on the left, and let's draw it as a diagram so it's easier to understand. So on the left, we see int x equals 61, right? So all we're doing is filling in some memory location with the bytes 61, and it would be 4 bytes. And this is called x. and each value has a memory location. So in this case, let's just say that it's in hex 0004, right? Now, if we look at int pointer y equals the address of x, all we're saying is we want this variable y, and we want it to store the address of x. We know the address of x is 0004, so we just put that value as y, right? And remember, any value will have an address. So even though y is a pointer itself, y has its own address as well, right? So now let's take z, which is the address of y, right? Y is a pointer to an int. So when we say z is the address of y, that means z is a pointer to an int, right? So let's take some time to think about what are the values of these expressions. Can someone tell me what x is equal to? Yeah, 61. Okay. What is and x? Huh? Yeah, it's the address. Then y is just the value that's at y, right? And y is the address of y. So 0008. Star y is we're following the pointer to y, right? So it's 61 because y is a pointer 0004 and it leads to 61, right? And then dereferencing z twice will go from the value of z, which is pointer to 8, and then we have the value of y, which is pointer to x. So 61. So hopefully that makes sense. Okay, let's continue. Arrays. So arrays and pointer arithmetic in C. So now that we have an idea of how pointers work, right? A pointer is just pointing to some value in memory, right? So let's think about this. All arrays in C are pointers, right? And where do we point to? We just point to the first element in the array, right? So if we have this code, int array of size 4 is equal to this array, 2, 4, 6, 8, then array points to the first element, so it's pointing to 2, right? That's what's in the red box there. And if we have an array, we can index using brackets. So a of 1 just gives you the first element. Well, it's 0 index, so you get 4, right? Okay, so what are the values of the following expression? What is the value of our array? What's the actual value? Any ideas? Yeah. Yeah, exactly. So the array is a pointer, so it's the hex value of 4. Okay. And then if we dereference that pointer, right? The pointer is 4, 0004, and dereferencing just gets what's being pointed to, right? So when we dereference, the value is 2. What about array plus 1? Array plus 1. What would that point to? Yeah, go ahead. Yeah, so it would point to 0x0008. And let's talk about why. It doesn't point to 0005, right? It doesn't point to 0005. It points to 8 because when we add 1 in C, we're actually adding the size of the element as well, right? And we're storing values of type int. So when we add 1, we're actually adding size of int. So we're adding 4, right? So that's why it's 0008. And then if we dereference this, we get the value that's at 0008, which is 4, right? Okay, quick reminder on endianness. there's big endian and little endian. And the way I like to think about it is big endian is we're writing out our value towards our higher address, towards the big end, right? So in this diagram, we have the value 0A, 0B, 0C, 0D. So we will write it going towards the larger end. So our lowest address will have 0A and our largest address will have 0D, right? For little endian, it's the same but reverse. We write it towards the small end. Okay. So hopefully this makes sense. Yeah. Okay. So the question was, if we're given some hex number, is that correct? If we're okay, sure. If we're given some 32-bit binary number, when we're like, let's say it represents some RISC-V instruction, when we're converting, do we assume that it's big endian or little endian? Right? So that's one thing I would like to clear up is endianness has nothing to do with the actual value of the integer, has nothing to do with the actual value. It just has to do with how it's stored internally inside the computer, right? So for practical purposes, when you're storing, you can usually ignore the endianness and just treat it as like a normal number, right? But within the computer, based on whether it's big endian or little endian, it might store it in a different order. So no matter what computer you're using, little endian or big endian, if you're storing some integer at some memory address, and then you're reading back from that memory address, it won't like suddenly switch the like order of the number at all, right? Because little endian reads in little endian, big endian reads in big endian. So this is just like something to watch out for, how it stores in memory. But at the end of the day, 0A, 0B, 0C, 0D will just be that same exact number, right? So something to think about, but the number will still be the same. So if you get this value and we ask you to translate it into RISC, you don't have to worry about it being like secretly some other value. It's just that value. Okay. So let's talk about strings. In C, strings are basically just arrays. And strings are pointers to one or more characters, right? And the way we represent strings, we represent it using characters in an array, and the null terminator tells you when the string is done, okay? So if I have some string like hello, right? That has 5 characters, but the last character is reserved for the null terminator. So it's actually internally, it's represented as 6 characters, right? So be careful when you're using malloc, right? Because it still assumes null termination, right? The size of a character in C is 1 byte, right? So yeah, this is the only size that is defined in C. Every other size is based on the size of a character, right? So size of a character is equal to 1 byte. And there are multiple functions that you can use to work with strings in C. One of them is strlen, right? And this doesn't include the null terminator, right? So this is how you call strlen. It returns the length of the string, excluding the null terminator. You can move string contents using strcopy, and this does copy over the null terminator. And this is the function signature, right? And your string contents can be compared with strcompare, right? And this is how you would call that. You pass in 2 strings, okay? So let's practice strings. So we have this expression, character pointer to str is equal to hello. Where is the first character stored in our code, in our memory? Where would it be stored? Any ideas? Anyone on Zoom can also unmute and say the answer.
Just add stir.
So I guess I should have like explained. I'll give this like first answer. It's stored in the static segment of memory. So I guess I should have said that I'm looking for like a segment in memory where it would be stored. So for this one, I'll just say it. It's stored in static because we're allocating a pointer to a string, right? So whenever we use the pointer notation, it's stored in static. Okay. For this line, where we use an array or like indexing operator, where is the first value stored?
In the stack.
Yep. So if you do it this way, then it's stored in the stack, right? How about this one, where we use malloc? Yep. So this one will be stored in the heap. And okay, so it's stored in a heap. Malloc strings are stored in the heap. Right. So let's do our first practice problem. This problem is from spring 2019. Basically, read through the description of the function and read through the code and what lines are incorrect inside this code. Why are they incorrect and how would you change it? Okay. And right now it's 8:32. So I'll give like 15 minutes to work on it. Okay, so hopefully that was enough time to work on this problem. So now let's go over the solution. So here's the solution. Basically, to summarize what this function is doing, it takes in an array, which is a pointer to a character, right? So you can imagine that it's an array of strings, right? And each string itself is a pointer to an array of characters, right? So that's why the array we pass in is a pointer to a character, right? And we pass in some size of our array. So basically what we're doing is we have some initial size that we're going to like use to, and this is the size of our output that we put initially, right? So, and we're going to go through each string in our input, which is array, and then we're going to copy that string over to output, unless the string of the input is stop. So we first allocate an output, right? Size of a character pointer, and this is a string, times the init size of our output, and that's how much space we're going to allocate. And then we initialize a indexing variable I, and while I is less than the size of our input array, we will iterate, right? So first we get the string that we're pointing to, which is character pointer, and it's called pointer. So pointer inside our for loop points to a string. And this is the first error. When we're using pointer, when we're assigning to pointer, we're dereferencing array and then adding I, when there should be parentheses around array plus I. So putting parentheses around array plus I gets the ith string, and then you can dereference to get the value, right? Okay. And then after that, at line 7, we have an incorrect method of comparison. So we want to check if our pointer string is equal to stop, but if we want to do that, we need to use the stir compare function, right? What this is actually doing is checking if they point to the same exact string in memory. They're checking this, what this code does is check if the address pointer is equal to the address stop. When what we actually want to do is go through each character, and if the characters are equal for all characters, then you stop, right? Okay. Let me get my charger. My laptop's running out of battery. Okay, so that's our next error. Our next error is in line 9, where we're resizing the array too late, right? In line 9, we're basically checking that I is not outside the like amount of arrays that we initialize, and our init size is 8. So that else if statement is actually checking when I is equal to our init size plus 1, right? We want to catch I once it hits index 8, because for a size of 8, the last index is 7, right? So we want to catch I when it hits the number 8. So we need to change that that line. Probably else if init size equals I should work, because then once we catch it, we multiply the size by 2, and then we need to reallocate, right? And that's our next error. In line 11, we can't just call realloc. We need to use the pointer that realloc returns, right? Realloc, the whole point of realloc is you pass in a pointer that was allocated using another function such as malloc or calloc, and then you put in a new size that you want, and then you get a new pointer back. Realloc takes care of that, right? But we're not using the new pointer at all. So that's our next error. And then finally for 13, when we're finally copying from our input array to output, we forget to malloc put space for our null terminator, right? So strlen, remember, doesn't include the null terminator. So you'd probably do strlen plus 1. Okay, so let's go to the next topic. This should be a quick one, operator precedence. So this is basically the idea of which operator comes first, right? So the difference between these two expressions, print x plus plus versus print plus plus x, is print x plus plus is doing print x and only then increment the value of x, versus the other one, which is increment the value of x and then print x, right? And usually the operator that's on the left is the last to be applied. So star p increment is equivalent to doing the increment and then dereferencing. This one is dereferencing and then doing the increment. This one is incrementing and then doing dereference. Okay. And this one is following the pointer using the arrow convention and then getting the address. So it'll do the operator from right to left. All right. So now let's go on to our next topic, structs and unions. Okay. So structs. This is an example of a struct. It's basically similar to objects in Java or classes in Python. Okay. So we initialize it by doing struct name, struct, then struct name, and then the name of the variable that you want to call it. So in this case, we would be making some object of type ex and calling it myStruct. So myStruct is a variable name, right? And now we can use the dot operator to assign to the fields inside the struct. So it has two fields, a is an integer and b is a character, right? So when we do myStruct.a equals 21, it just sets a to be 21. MyStruct.b equals z sets that. And if we use, like any other value, a struct has a pointer, has a memory address. So if we use the AND operator, then, oh, it's not charging. So if we use the AND operator, what it's doing is getting a pointer to the struct. Is this charging? Okay. Okay, I need to find a way to charge this laptop somehow. Oh, on the side here? And for some reason, the outlets that are provided here are not working. Okay. Huh. Okay, so we have a problem. There is a time limit on this laptop. It's at 5% right now, and the outlets at the stage do not work. So Liam, oh, there's some here. Maybe these will work. Okay, cool. Found an outlet that works. Okay, so my laptop is charging. We got it at 3%. Let's continue. Again. Okay. Okay, it's charging. Okay, oh, Zoom is taking a lot of battery. Jeez. Okay, so let's continue. So now that we have an idea of structs, here's a warning. Be careful with your functions, right? So let's say we are given myStruct. We already set it up and initialized it. And say we want some function, func a, that should modify the struct that we pass in, modify the a field to be the value 4, right? What is the issue with calling func a myStruct, right? So this is where we pass in the struct directly. There is an issue with this, right? So let's talk about it. You got to be careful with your functions. So this is an example of an incorrect implementation of function a. And remember, function a, all it does is set the a field to be 4, right? So this is wrong, right? To see why it's wrong, let's call it. So let's call func A on my struct. So we enter the function, right? We pass in this argument, the struct argument, and once we call the function, we make a copy of what's passed in. So it actually makes a perfect copy of my struct, right? And then on the copy, it edits the A field, and then it returns, right? And deletes the modified copy, right? So the copy was edited and then thrown away, and the original struct was unchanged. So the way to avoid this, pass a pointer whenever you want to retain your changes, right? So if you ever want to edit something using a function, you pass in a pointer to that thing as the argument. So in this case, instead of passing in the struct, we pass in a pointer to the struct, right? So star pointer gives you the object itself, and then you can use .a, or you can use this other notation with the arrow. They're the exact same, okay? Okay. So one way to remember the arrow operator, it just means follow the pointer to the field, okay? So now it works as we intended. So if you want a function that changes some variable x, the function should take in a pointer to x. Key idea, okay? Okay, let's talk about padding with structs. So for any struct that we have, the fields of the struct are stored in order, right? And we align each field with size of the field. So for the first field, which is A, we align it to line up with multiples of 1. So basically this can be any like byte in memory. For B, we want to line it up with multiples of 4, right? So it can start at, field B can start at 0, 4, 8, so on, right? And then C also just lines up, you can put it anywhere. Okay, structs themselves are aligned on addresses divisible by their largest field. Okay, question? Okay, so the question was, what does it mean to align each field with the size of the field if each field has a different size, right? So basically what a struct is it stores all of these fields inside memory. So you would just go through each field. So like in this example, A, you would have to align it with, so what align means is where can we store this field in memory, right? Where can we store it? What multiple does it have to be on? So it has to be on a multiple of its own size. So character is size 1, so it has to be on a multiple of 1, right? So it can be any number basically. For B, has to be on a multiple of 4, right? So it can be 0, 4, 8, and so on. There will be an example. Okay, so in this case, the size of the student struct, are there any like ideas what it could be? And it's okay to like have a wrong answer because we'll go over the solution. And reminder, if you're on Zoom, you can just unmute and say the answer. Go ahead. Okay, so student answer was 6 bytes. Are there any other answers that people are thinking of? Yeah. Sorry? 12 bytes. So we have 6 bytes and 12 bytes. So let's take a look. Oh, yeah, go ahead. Okay, so we have 6 bytes, we have 12 bytes, and we have 9 bytes. So let's think about it. The size is actually 12 bytes, right? And the reason that it is because we are storing each field in the order that it's put in the struct. So we would first look at A and say, okay, I want to store A, we can store it right at 0. And then we go to B, right? It's an integer, has to be stored on a multiple of 4. So we had to put it at the 4th index, right? And then once we hit character C, we look and we're like, okay, we can put this character anywhere, so you can store it at 8. And then the size of the struct has to be divisible by the largest field in the struct. So 9 would be the correct answer, but we need the struct size to be divisible by the largest field. The largest field is 4, so we can't use 9. Instead, we round up to the nearest multiple of 4. So 9 rounds up to 12. Right. So now let's reorder it. We have character A, character C, and then integer B. So now what's the size? If you're on Zoom, you can just unmute and answer. And in person, you can just raise your hand.
It's size of 8.
Okay, so one answer is size 8. Another answer? Okay, another answer is 6. So let's take a look. And the size is 8 bytes, right? And it's very tempting to say the answer is 6, but one thing to note is that we're not packing all of them immediately together. So if we did pack them, then it would be 6 because you just add 1 plus 1 plus 4. But because we're using this padding technique, we store A in 0, store C in 1, and then when we try to store B, we have to store it on a multiple of 4, right? So it would be total 8 bytes. Okay, quickly let's cover unions. Yeah, go ahead. Could you repeat that? So the place where we store something is dependent on its size. So for an integer, which has size 4 bytes, we want to store it on multiples of 4, right? But for a character, the size is 1 byte. So we want to store it on multiples of 1, but every number is a multiple of 1, right? So we can store a character anywhere. Question in the back? Okay, so the question was, what's the actual difference between packing and padding? And there was some mention as to the max of the field size and the minimum of the field size. So the difference between padding and packing is where we just take each field and squish them together in memory to take up as little space as possible. So if we were packing this struct, we would just do character A is 1, character C is 1, integer B is 4, and then that green segment would just be right next to the blue segment. So that is packing. Padding is where we want to align our fields with its size. So for that reason, in this situation, the int is aligned with 4, right, which makes the size 8. So that's the difference between packing and padding. Another question?
Yeah, what happens if you have a pointer something, or not a pointer something that within the struct that you allocate? I'm not sure if that's possible, but should you allocate something then?
So what is the intention of what are you trying to do basically?
I was just curious,
Uh-huh.
the allocation would work, or would it just be that you have to store a pointer and
Yeah, okay, so good question. The question was, how does reallocation work with reference to structs? So basically the typical case or typical use case is we would have some struct, right? And you can get the size of the struct using a C function, which is size of, right? So if we want to allocate one side, space for one struct, we would do malloc then size of struct, whichever struct it is. And then let's say we have that pointer and we want to store two structs, right? You would just pass in the original malloc pointer and then put the size of struct times 2. And that can hold two structs. So that's like the typical use case of realloc with reference to structs. So hopefully that makes sense. Okay, then let's continue. Let's talk about unions really quickly. I would say this is less important, but it is a common C function, right? So unions are basically just like structs, but instead of holding a bunch of values, it can hold one value at a time. So the size of a union is equal to the size of its largest field. So if we have this union, the largest field is that giant array. So the size is 40 bytes. And we can use the dot operator just like a struct. But when we assign a new value, it erases the other value. Okay. So let's talk about memory structure. Hopefully I'm on time. The time right now is 9. Let me see how much I have left. Okay. Okay, we should be good. So let's talk about memory structure. So our memory structure in C is where do we store which variables? That's the basic idea. And we have 4 different segments, right? One of 4 segments, there's code. And this is your actual program. It will be filled with like, let's say RISC-V instructions. It doesn't change in size over the course of the program. And there's another field, another segment, which is our static data, right? This is our memory for the entire program, right? It doesn't change in size either. It's static. The size is static, right? And then we have stack. This is very common. It is dynamic memory, and it is associated with functions. It lives with a function call, and it holds the local variables for the function. So this would be the arguments and function and any arguments you pass into a function, and also variables defined inside a function. So local variables. And it grows from the top down. And then finally, we have our heap. This is also dynamic memory that the programmer is in control of. You use your memory allocation functions, so malloc, calloc, realloc, and then you free that memory using the free function. And it grows from the bottom up. Okay. So code is the code that you're executing. It's in read/execute memory, right? Static is basically constants that don't need to be changed. So, and this is stored in RAM, right? Random access memory. And this just refers to the state of memory. And it retains memory for as long as power is supplied. So like if your computer dies, like mine almost did, then it would basically lose its RAM because RAM needs power to store. Right? And this can be changed, actually. So even though there are constants that don't need to be changed usually, it can be changed. So we have the heap. This is the most important one. It's memory that's dynamically allocated by the programmer. It is read-write, not executable, and it must be freed. And if you don't free it, what will happen is each time you call your program or run your program, it will take up a tiny bit of memory, and then eventually you'll have no memory left in your computer, and that's a problem, right? It grows bottom up, and stack is similar to heap, except it's related to functions, grows from the top down. Okay, so let's talk about memory management. Basically, the main one major point in C is that the programmer is responsible for storing and taking care of memory, right? Other languages, you don't have to worry about it. There's a garbage collector, but in C, you are the garbage collector, basically. So use the alloc family of function. Malloc takes in a size of bytes to allocate and returns a pointer. And this memory that you get a pointer to is not zeroed out. So it will hold garbage values initially, right? versus calc, where you put in a number of elements and an element size, and it'll calculate that, give you some pointer to a number of bytes, and they'll all be zero. They'll be zeroed out. Okay, and then finally, realloc, you pass in a pointer to an existing like malloc or calloc region in memory, and then say, this is the original size. I want it to be this size now, this new size. Right. And if the size is too big, it might actually like move your pointer in memory. But if it does this, it'll transfer the memory anyway. Okay. And a small note is that malloc, calloc, and realloc, they don't store things in memory like one by one by one. It will like try to fill in the gaps in your memory as possible. Okay, and then another important function is free, right? So free is used to make memory available again. So it takes in a malloc or calloc pointer or realloc pointer. It must be used once per pointer, right? And then if you don't free, it's called a memory leak, right? And if you free a pointer twice, it's a double free. So each pointer that you have, free it exactly once. And if you access freed memory, it's possible because the system doesn't like make any guarantees. You didn't ask for the space. It'll have possibly undefined behavior. Okay, so our next practice problem, the time is 9:07. I think I'll give like 5 minutes for this one. So work until 9:12 and then we'll go over the answers. All right. Okay, so for the people on Zoom, there was some like Wi-Fi cutout here. So hopefully everything's back on track. I think it should be recording. Okay, yeah, it is recording. So let me share my screen again. Okay, can you hear me now? Awesome. Cool. Okay. So yeah, use this time until 9:12 to work on the question. Let me share my screen. Host disabled participant screen sharing. Okay. I thought I was the host actually, so let's see what's going on. Is there a staff member in? Oh, okay, I see what happened. Okay, so my Zoom shut down and it made a random select person host. So congrats to Amog Tantradi. You are the new host. Okay, so let me figure out how to fix this. Yeah. Liam, can you help me out? Okay. Okay, the host, Amog, the host, has allowed share screen. So I think it should be good. Hopefully, let's see if this works. Awesome. Okay. Can we get a round of applause for Amog? Okay, this is the first time that's ever happened. Wow. Okay, so I'll let you guys work. All right, so it's 9:12. So let's go over this question. So basically the question is, where do these values sit in memory, right? So let's go over the answers. All right, so let's read through the code and figure out why the answers are what they are, right? So stir1, let's find stir1 in the code. It is a character pointer towards the middle of the code, right? And it's assigned to the string. So stir1 will be an unchangeable string that can't be modified, and it will be in the data segment, right? It will be data, or I think the other word is static. Yeah, data/static. Either answer will work, right? For n, so we look through the code and we see n is a argument inside the function copy n bytes, right? So in general, if it's in a function, then it's usually in the stack, right? For stir2, we can look inside the main function and we see stir2 is assigned using the array notation. And if we use an array notation, then we know it's in the stack, right? Stir3 is allocated using calloc, right? So for any variable using those functions, malloc, calloc, realloc, it will be in the heap, right? And then stir1, the variable itself is inside the data field, right? And then the address of stir1 is inside our text. The address of stir1 is inside our text. What is? So basically, this code itself is inside our memory, right? And we have a variable called stir1, right? So it's basically asking, where is that variable defined, right? Where is that variable defined? And that variable is inside our code itself, right? So the address of the variable is inside our text segment. Question? Mm. Mm. So, okay. So the question was, isn't stir1 itself a pointer? And pointers that are assigned like this with the character pointer notation, aren't they just stored in data/static? So yeah. So yeah, shouldn't it be in static? So I guess basically the main idea is that any variable name is just a nickname for a value, right? So stir1 itself is some value, right? And the value is a pointer to the string, right? So stir1, the pointer to the string is inside our data segment. It's like static, right? But the stir1 like variable itself, right? Stir1 itself is a variable, right? And that variable is defined within our code, right? Mm. Mm. So if there's a variable that's defined in main, it would actually be like a stack variable because main itself is a function, right? So I guess your question was like, what if it's like a global variable, right? Yeah, yeah. Yeah. Question? Do you reference stir two? I think I want to double check that before I say anything. So if you want, come to me at the end of the session and then we'll talk about it. Okay. Sure. And if you want, you can also post on Ed and someone will get back to you. Okay. Okay, so for this last topic, which is call, I'm inviting Liam to present it. On the mic. Yeah, you just get on your pants. And then you can clip this onto your t-shirt. On your t-shirt, yeah. And yeah,
Just arrows.
yeah,
Yeah.
sure.
Check, check. Can the back hear me? Good. How about Zoom? Sweet. All right. So I'll be presenting or reviewing the last section of the session, which is the call stack, which by now you may by chance know stands for compiler, assembler, linker, and loader. But before diving into the call stack, I just wanted to take a step back and address or talk about just general language execution and specifically language translation. Whenever executing code that we're writing, it's commonly translated before it can actually be performed on a machine, which language translation is taking source code, typically in some higher level language, and turning it into something readable, either by a machine or by an interpreter, which then addressing what an interpreter is, it's a program that executes a source program, something that you're wanting run. And then on the flip side of things, a compiler is a program that produces an assembly file from source programs, the program that you're wanting run. And historically, or just typically, we interpret higher level languages such as Python and compiled lower level languages such as C. But both of these terms are considered translation. They're both code translation. And then I'd also wanted to touch just a little bit on a specificity that it's not an actual language that is interpreted or compiled, but the implementation, such as C is typically compiled. Just we compile C programming in this class with GCC. But there's also implementations now that interpret C. And then just specifically some pros and cons of each. Interpreters are versatile, meaning they have independent instruction sets, AKA an interpreter when packaged can run a language both on Windows or Mac, doesn't matter. Interpreters are typically simpler to write, but typically slower than in executing similar size code than a compiler. And then compilation, as I just noted, is typically faster at executing similar size code as an interpreter, but compilers are notoriously hard to write, and they're also not portable. And that is due to their optimization for specific hardware. And then I also wanted to note just another specificity that we have the umbrella term compilation, but it really is only the first step in that call stack. You either interpret or you go through the call stack, but we just typically reference that whole stack of functions as compilation. And then I had the first question just regarding language execution, which I will let you think about for a second. And then if anyone wants to answer it, you're welcome to. Oh, whoopsies. There we go. give the options here. Anyone have any ideas? What do you think? In the back. Yeah.
Space.
Okay, good job. Yeah, both of them. Oh, there was another option here. I'll jump to the answer of the first one first. You were right. The second one and fourth one are both correct, but then also the third one is correct. And then I'll give you a minute to pretend like you didn't see the answer to the second one and think it through. And then, as you guys just saw, only the last one is correct. Compiled code generally is only able to run on one instruction set architecture. All right, before jumping into going through the call stack, I just had a couple questions, a little sanity check. If someone wants to try and give me the answer for the first one on whether it's the compiler, assembler, loader, or linker that handles that first step or has multiple inputs of hex code. Any ideas? Okay, I'll give you this one. And I'd emphasize the multiple. Whenever seeing that, think linker, and we'll touch on that again. And then running through the rest of them just quickly, takes C code and converts to assembly. That's compiler. Think if it's getting converted to assembly files, which is handled by the assembler, the step before that's a compiler. And then outputs binary files, that's the assembler. Calculates absolute addresses, linker, and allocates memory for executing, that's loader. And then I would say that this slide is probably the most fundamental to the call section that I'm presenting. So just getting this slide memorized or just in your head. That compiler takes lower level language to assembly language, and specifically in our case, this class that's C files to RISC-V files. The assembler takes assembly language and converts it to object code, which is those RISC-V files to object files, which have the extension .o. And then the linker takes object code and turns it to an executable. And finally, the loader takes that executable and loads it into memory for execution. So first, the compiler. The inputs are a low-level language, typically, which in our case is C. The output assembly file, as I just mentioned. And then just some specifics. The compiler takes our written language, such as C, and optimizes it and turns it into an assembly file, which it does by tokenizing different chunks of that C file and turning it into sort of an abstract tree that is then able to identify some program structure and just organizes it in the most efficient way possible, which that really is edging on out of scope for this class, but just know that the compiler takes our C files, turns it into assembly files. And then it also checks for semantic errors, and as I mentioned, possibly reorganizes. And the assembly file will have labels, pseudo instructions, and fully relative addressing. And then this is something that you could definitely put on your cheat sheet just to know the pseudo instructions to quote real instructions or base instructions. Some common ones are the move or branch branch equals. And these slides again are posted, so this is something you can write down at a later time. Then moving on to the second step of the call stack is the assembler, which its inputs are an optimized assembly file or files. Object files are its output, and specifically it generates these files by going through the code with 2 passes. In our case, there are some 1-pass assemblers, but in this class, we only deal with 2-pass assemblers and creating 2 tables, the symbol table and relocation table, of which on the first pass, it replaces pseudo instructions that we just went over, like move or load address, and with their base instructions. And then it gathers labels for the symbol tables, such as different branching labels that you may have put into your code. And then on the second pass, it generates the relative addresses for those labels and replaces them. And then it actually generates those object files. And I'll emphasize that the 2 passes is necessary because of forward referencing, such as a branch statement branching to a label that's later down in the code. And the compiler runs line by line, so it has yet to see that. So it adds it to the symbol table and then later fills that in. And then this again, I would not say is imperative, but another thing that could go on your cheat sheet, common general directives, which directives are keywords of sorts that give directions to an assembler, but do not produce any actual machine instructions, binary output to the final object file. And then again, those are just something that you could write down and know on your cheat sheet. And then specifically, I wanted to touch on both the symbol table and relocation table, which the symbol table first is the one that is dealt with completely in the assembly stage in the 2 passes. And you can think about it as just, this is the stuff that I have, as in the specific file that's getting compiled at this time. Such as an example, let's say we have file A, the native file, and the symbol table is used to replace forward referencing, like we just mentioned. And then on the flip side, let's say file X, that's an external file, uses the symbol table to replace its own external references. So if it referenced labels or functions in this file A, the symbol table would be used to replace those references. And just specifically an example in C are the include directives that import libraries and such, or external functions. And again, generally what goes into a symbol table are labels, like I mentioned, data, anything with the .data directive, or variables which may be accessed across files. And then the relocation table, I would emphasize that this you could think of as the stuff that file A couldn't find. It's the list of items whose addresses aren't in said file and need to be found. And what do these items or labels commonly include? Any absolute jump using JAL or JALR, sometimes internal labels, external labels, including library imports, load address instructions, and then any data in the static section. And then this table isn't fully dealt with in the assembly stage. It is used or completed in the linking stage. And then linker, second to last function in the call stack. Its input files are object files and its output is an executable. And then generally, or in a 1-line summary, it links files, text, data, and relocates necessary addresses. It combines text from different object files, places that data from the object files in one file, and then it organizes all of the things it's linking in 3 segments: code, or text, data, and headers. And the headers specify location and segment sizes. And then also, as I mentioned, resolves references in the relocation table. And then finally, the loader, it takes that executable and output is, I put quotations memory because there really is no real output. It finally loads that executable into memory. And then finally that function is run or program. And so specifically, it sets up the necessary space for loading that text and data segments into memory. And it initializes the stack to hold arguments from the program. It initializes registers, clearing them, sets the stack pointer to the highest position, and sets the PC register. And then additional routines that are, again, just out of scope. And then to recap and just retouch specifically on outputs, the object files from the assembly are .o files. That's the general extension. And their composition is made up of size and position of the later components, the data and text. And specifically, the text segment holds machine code, and the data segment contains a bin of all the static data. And then the relocation and symbol table and some debugging information. And then the composition of executables are again simplified through the linking process. And it contains a header, which has the size of the text and data segments, and then the text and data, and then that executable is loaded into memory by that loader. And then here is the first major question of from the spring 21 midterm. And it's just a true false. And I'll give you a couple minutes to read through each instruction and then give me a true or false for each one. I'll give you 2 minutes-ish. All right, give it a go on the first question. True or false? So feel free to chime in. Can you show handles them? How about now? Yeah. That, yeah. This one? Yeah. Yeah. you hear me? Any clear, Zoom? Oh. Yeah, okay. So does anyone have a answer or a try for question one? Yes. What? False? What? Can I put you on the spot and ask why? You think that? Yeah, perfect. Yeah. How about question two? Question two, what you say? Just like he said, that there can be other compiled or another assembly such as x86 compiled into this guy. That's just more of the specificity with this prompt that we're doing. Proof for number two. Yeah. And that's due to object files contain a header which has segments like we talked about earlier, text, data, symbol table, etc. And then the exercises. And then three. Yeah. That again. Just like we talked about, the worker builds that executable and all the object files. Four. Yep. Yeah, exactly. Those pseudo instructions. How about five? Yeah. Correct. Just like we talked about that the
They
the
say
mic
your
is not clear.
USB. Shut down.
One. Check, check. Any clear? Yes.
Okay.
Okay. I wonder. Yeah, I don't know what. Maybe I switched it by accident. Oopsies. I'll give the rest of the answers here in the explanations. Oops, went too far. And if anyone has any questions on any of the explanations, I'd be happy to answer, or any questions in general thus far. 6. Sorry. All right, we'll go to the next set of questions I have for you, which is just a sort of summary on what each stage is function is. So for each question, just select the either compiler, assembler, linker, or loader for if that respective command or thing it's doing belongs. And I'll give you a minute or two to look over each question. All right, we'll start with the first one. Select the stage that computes the offset for example branch equals instruction. What do we think? Assembly? Correct. That's exactly right. Just because of the fact that a branch equals instruction is going to be relative addressing. And so on that second pass, we're going to fill in that address. And then for B, select the stage that computes the offset for a jump and link instruction to a function of a different object file. Linker? Exactly. And I'll emphasize again that when you hear different file or multiple files, I jump to thinking linker. And then for C, select the stage that creates a symbol table and a relocation table. Assembly, yeah, exactly. And then I think of that just like tables. When you buy them from IKEA, what do you have to do? You have to assemble them. Assembly makes the tables. For D, select that stage that emits, add register S0, S1, S2. What do we think? Like output, that's its output of the file that would contain that. Compiler, exactly. Think C to RISC-V in this instance. And then finally E, select the stage that combines several object files into a single executable. Linker. Yeah, exactly. And again, just multiple things, multiple files, linker. Whoopsies. Oh my gosh. I guess so those are the answers that we just went over. And then the next final question. Zoom's taking some CPU power and a computer slowing down. Let's see. Okay. So for this last question, it might take a little more time, but go through the code base that we have on the left of the slide and then try and fill in the symbol and relocation table. This would be essentially what the assembler is doing. And so for the symbol table, just think what goes in symbol tables. Is it labels? Is it instructions? What goes there? And then for the relocation table, do the same thing. And it gives you 2 examples to start with. And I'll give you a couple, 2 minutes, 3 minutes or so. All right. Does anyone want to volunteer and take a stab at something that would go in the symbol table? Let's hear it. Yep. Yep. Yep, exactly. That's perfect. And then relocation table. Anyone else want to give it a try? We're on Zoom. I'll just go through the last bit, the relocation table. So again, I would look back on the slides and we saw that instructions such as load address always require to be put in the relocation table because the address is actually in the data segment of memory and the linker has to put that address in. And then also the JAL printf statement that's referencing an external function. The printf function isn't in our file. That's a library function. So again, the linker has to handle that contingency. Yeah. Exactly. So the J check, the check is a local label or in the same file. And so on that second pass of the assembler, it will fill that in the symbol table. So on the first pass, it's going to see that check as a label and put it in the symbol table. And then on the second pass, on that J check, it'll put the address of check like in that instruction line of the jump. So the actual STR is in that program file, yes, but the address of 0x80, that address is actually stored in the the data segment, if that makes sense. It was sort of the dilemma we were Nitin was talking about earlier with the string literals and such. Yeah, of course. And then that was it for the call section. I would end with any questions on any of that or confusion. That I believe is due to the data directive. It is actually like after the text or code in addressing. Any other questions or on Zoom? So Gabriel asked, just to address the question, isn't the address on the relocation table a question mark for printf since the address for printf is in another file? Yes, the addresses are actually just referencing what line the relocating needs to take place. So the relocating of the absolute address, it needs to be relocated into address X028. And then again, the J check was a program counter relative jump. So that is able to be handled with just the 2-pass assembly and thus in the symbol table. Alrighty. Nitin, do you want to, I can come to you if you'd like, if you have any. Yeah.
Okay, so there was a question about a student question about a previous slide that I'll explain. And it was pretty confusing. So let me go back. It's back here. It was regarding where is stir1, the address of stir1 encoded? What point in memory is it stored in? So I think it's somewhere here. Okay, here. So for the answer for address of stir1, I did ask Peyrin on course staff, and this is the answer that was given. I was actually like not too sure. I had a general idea of why it is, but basically the address of stir1 being in text is implementation and compiler specific. So he says, my guess is that the address of the stir1 pointer, right? Stir1 is a pointer to a character, so it's a string. The address of the stir1 pointer gets encoded in some instruction when the function call uses stir1 as an argument. Okay, so basically if you find it, so like your code is instructions, right? Your C code gets converted to RISC-V, and those instructions are stored inside your code segment. So he's saying that when stir1, the address stir1 is used in a function, that gets encoded into the instruction, right? So for that reason, the address of stir1 is encoded inside the code. So if that was confusing, please don't hesitate to post on Ed. But for now, that's the end of the review session. And if there are any final questions besides that, then I'll take them right now. Or if you want to post on Ed, that would also be fine, and we'll get to the question later. Questions?
Yeah, so. Just like the question that asked before, so the actors of the third two also like the staff. What they expect. In the implementation of the structure. That's not right.
I think it gets kind of confusing. I don't want to answer it right now because I'm actually not too sure, but do some research into it after the fact and I'll get back to you. Okay. I'm gonna hit pause on the recording or stop